All right, all yours.
Okay, great. Okay, so thanks everyone for coming. We're really excited today to have Michal Oszmaniec with us, who is going to tell us about saturation and recurrence of complexity in random quantum circuits. Take it away.
Yes, thanks, Bill, for the introduction, and thank you for inviting me to speak about this work that is actually not yet on archive, but it will be out eventually. Yes, so as Bill said, I'll be talking about saturation and recurrence of complexity in random quantum circuits. And it's a joint project together with Nick Hunter-Jones from Stanford and Michał Oszmaniec from University of Gdańsk. Yeah, I mean, okay, as I mentioned, I actually ended up putting most of the social arguments for our proofs. My motivation will be quite brief. And okay, I assume that actually you guys more know about those connections to gravity than I. So let us just get started straight with this Brown-Susskind conjecture. That is, as far as I understand, in its original form, conjecture about unitary evolution of some quantum chaotic system. So you have some Hamiltonian, let's say chaotic many-body Hamiltonian in n-qubit system. It evolves with, the system evolves in time, let's say it's isolated. But now, you can, if you come from quantum information background, you can, okay, like we define now complexity of some unitary transformation as number of elementary gates that approximate you to accuracy epsilon in some notion of distance. I'll be defining those things precisely later. And now, I guess around 2016 or 2017, Brown and Susskind conjectured the following, let's say, a picture of evolution of complexity of generic, say, many-body chaotic system. Okay, so you know, when this time is very small, you're very close to identity, so your complexity is very small. So you start with zero complexity or trivial complexity, and then the complexity is supposed to grow linearly with time for exponential amount of time until it saturates. Because if we are in a finite dimensional system, I mean, there must be some limit of our complexity. I will be talking later, like why is that precisely, but then it saturates after some exponential time. And they expected to have this recurrence, so coming back of this complexity to the trivial value around, again, okay, now double the exponential time with the system size. And yeah, just regarding motivation, I guess you guys know more much than I do about it, but so motivation for study those many-body chaotic systems in this in those time scale, they come from attempts to apply ADS-CFT correspondence to evolving wormholes that connect to two copies of anti-de Sitter spacetimes. Okay, and so those wormholes they are supposed to grow, or their volume grows on a classical level, like abundantly with time. And people, especially I guess Brown and Susskind, were wondering what should be the corresponding physical quantity on the conformal theory side that corresponds to this growing volume or some other object like action on the gravity side. So they put like on the quantum realm, there are not so many quantities that are like, if you're in a finite dimensional system like that can grow grow for a very long time. So like they conjecture this complexity. Okay, so somehow this it's supposed to correspond to some quantum mechanical phenomena inside those black holes. Yeah, I'm sorry, I cannot say more about you guys much more than I do about it. On the now more like okay, side that I understand, if you have some chaotic system or like any class of physical systems, you might be interested in pinpointing some universal proper characteristics of it. Okay, so it's always nice, in statistical physics when we have some, universal critical phenomena or universal behaviors of physical systems. So this picture that of complexity evolution is it's in a sense like universal prediction about long-time behavior of such systems. So it would be nice to have a proof or understand it. Right. Just regarding this conjecture in the original form, there are of course problems to attack, to solve, to prove it rigorously. So first, it's notoriously difficult to compute complexity of a unitary or a quantum state. And one can relate it to some complexity theoretic conjectures. And I mean, I'm not gonna enter into weeds here, but that's it's difficult to just because you essentially I guess you cannot do much better than just try all the possible circuits that would approximate your gate or your state. And complexity of such procedures is exponential, so it's hard to do. And also there are not known unconditional lower bounds for complexity of unitaries that are generated by some Hamiltonian flows. Okay, so this, let's say, those problems motivate to study maybe some toy problems that would be more trackable or amendable to study. So specifically, one can look at this conjecture for other models of chaotic evolution, like random quantum circuits. So random quantum circuits are constitute this model that was widely studied in many contexts in quantum information. And it's supposed to mimic somehow at least some features that this chaotic evolution many-body has. So it's defined as follows. I will be defining again those things more formally later. So now the role of time is played by the depth of the random quantum circuit. So you have a unitary UT that you obtain by concatenating T layers of random gates that are local, and let's say couple at random different qubits. Again, I will be defining those things later. So by local, I mean that they act on at most constant number of qubits at the time. Right. And in this context, one can study the same. I mean, one can ask the same question, what is the behavior of complexity of unitaries generated in this random fashion? And pretty much the same curve is conjectured. That is to say, you have this phase of linear growth, saturation, recurrence. And let me discuss some previous works that attack this specific problem. I mean, by the way, if there are any questions or comments, please do not hesitate, because to ask. Okay, so right, so recently there was this very nice work by Jonas Hefferstab, Ian Seizert, a bunch of other people that proved actually this this conjecture for the specific case, and I want to, let's say, emphasize this, when the accuracy parameter that define the complexity is 0. So we are talking about complexity of exact implementation of quantum circuits. And they were studying qubit architectures and I guess one-dimensional architectures, like in a sense that you know, qubits were arranged on a line and just neighboring ones were sort of talking to each other, and they did manage to prove linear growth up of exact complexity. And until some exponential time. Right, I just want to say, I mean, it's a very nice result and I love the paper. It uses some nice tools of algebraic geometry. Just physically, it's a bit, I mean, there's still, I mean, it makes sense to go beyond epsilon equal to 0 because basically just by dimension counting argument, you know, in the vicinity of, let's say, identity channel or identity mapping, like you take any small epsilon, as small as you want, and you will always find there unitaries that have, let's say, maximal or exponential exact complexity. Even though your physical error is exponentially small or like ridiculously small. Okay, so it really makes sense to go beyond epsilon equal to 0 from the physical point of view. Another work I should mention in this context is a paper by Brandao, Nick Hunter-Jones, a bunch of other people, Richard Keng as well, that did study approximate complexity in the early time regime. And they managed to prove, say, sub-exponential growth, sublinear growth of complexity for small times. They also studied somehow stronger, relatively strong notion of complexity. Right. So this is, let's say, more or less state of the art regarding this problem, and here are our contributions in this project. So, so first, so we focus first of all, yeah.
Just to understand, so I mean, you've shown us that there were two what sounded like conflicting results. Is it that they were literally defining different complexities, or
no?
So
they concerned, different complexities, right? So it's a bit not unfair to put it on the same figure even, but
right.
But okay, I like, let's say here I should say it's the complexity is lower bound, so they gave lower bound on the complexity growth. Mm-hmm. Okay, so the true behavior can be anywhere like above. Okay, so it's in that sense not conflicting. I mean, okay, it's like it's not fully fair to put them on the same kind of plot. Okay?
Right. Fair enough. Yeah. Okay. Good.
Because like, yeah. But let's say for fixed epsilon you can put, and so in this work we focus on the, let me check the time, yeah, on the I should speed up, okay, on the long time regime. So we study first saturation of complexity, that is, we want to understand timescales on which maximal complexity that is available in the system is attained in this model. Yeah, and actually we prove some results about it, both about the saturation time and about maximal value of complexity. Essentially, I'll be discussing results later in detail. So second, we prove the recurrence. That is to say, we show that as we are looking on, let's say, different trajectories of this random walk that we have in the space of unitaries, after this double exponential time that has this dependence on epsilon, the error, with overwhelming probability, your walker, your unitary or state, its complexity will go back to 0, okay? In time, that is scaling like this. So, okay, after this long time, you are certain, visually certain that complexity went to 0. And lastly, we also, to some extent, are able to pinpoint the timescales on which recurrences occur in this model. So here, as expected, the timescale is double exponential, but the event itself lasts exponential amount of time. So this we kind of, in probabilistic sense, are able to capture in this model. Any questions? I mean, okay.
I have sorry if you've already covered it. I was actually slightly distracted because I was flipping through the Haferkamp et al. Article as you were talking about it. And you were specifying that they made an assumption about epsilon being 0. I don't actually see an epsilon in their paper, so I'm wondering if you, and you undoubtedly said this, and so
okay.
Distracted.
Okay, I actually, it was published in a very good journal, right? Like in Nature Physics. I remember looking on some archive version some months ago, and like maybe the paper got, you know, stripped. I mean, I do. So they study exact complexity, okay, because to begin with. So this is maybe one of the reasons why epsilon doesn't appear. They have, okay, if I'm at some point they have some qualitative, some statement that it's some like that it, in some sense it's possible to extend in, but it's not very precise in what's like beyond epsilon equal to 0.
My question is much more naive. I'm wondering, I'm also looking at the archive version, by the way, the what is your definition of epsilon with respect to them? And is it the same epsilon that you have lower down in the current slide?
Right, so here I haven't yet formally defined. I will be talking about epsilon measured in, say, diamond norm. So some golden standard distance between unitaries. With unitary channels, yes, and okay. Those, yeah.
Okay, so I'll wait for the definition of your epsilon and assume it's the same as is in your current work. What I'm also wondering, to anticipate slightly, if you could give us some intuition for why this complexity ultimately decreases, because you know, a naive intuition would be that it just should, you know.
Right. I will attempt to give even a proof together, I mean, in the form of intuition, maybe, or a sketch of the proof. So maybe, but.
Now wait.
Yeah. All right. Thanks for the question. So, okay, formal definition of complexity, right? So, right, so we have a system of n-qubits with local dimension q, and so we will define complexity with respect to some fixed universal gate set that consists of 2 local gates. That is to say, gates that act at the same time on 2 qubits only. Right, and now when we have, so we can build sequences of gates from those sequences of unitaries from those gates. And now when we set some parameter, like we can look on, let's say, words or unitaries that one can obtain from concatenating, let's say, are such gates with each other. Okay, so this is a like set. This GR denotes set of words built from gates of from this universal gate set G. Words that have length at most R. Length R. And now unitary complexity is a minimal, is defined as the minimal size on the scale epsilon, is defined as the minimal size of the circuit R that is needed to approximate a target unitary U to accuracy epsilon in diamond norm. A diamond norm, okay, you can take many different norms in the space of quantum channels. This is some usual norm, okay? Does it make sense? So yeah, this is the complexity we work with in this project. Right, and now local random quantum circuits.
So sorry, as you pictured, is the diamond norm just an L2 norm?
No. All right, there is, look, I want, right, so we wanted to be kind of kosher or physical here. So we are cautious to work on the space of unitary channels, but fundamentally it doesn't matter that much. You could work formally in the space of, so space of unitary channels is formally a isomorphic to projective unitary group. So you need to do some quotients, like you can do some quotients to use like L2 norm on the projective unitary group as well. Yeah, I mean, we did it for channels. It's possible to, I guess, repeat almost everything I'm saying on groups. Although I want to emphasize that channels are, okay, formally more physical because, like, for example, global phase of a unitary doesn't have physical relevance. And it shows up when you compute, like when you just compute L2, like Hilbert-Schmidt distance between unitaries. Okay, I mean, okay, this is some, I mean, it leads to some technical complications, but really, I mean, please ignore it, like if you can. Yeah, okay. Okay, so random local quantum circuits. So we have random walk in the space of unitaries that is generated by some measure in the space of unitaries, this measure with superscript G. So this superscript G stands for a graph that will be encoding connectivity of my qubits, or like which qubits I will be sort of coupling to each other. And the way this model works is that in any specific step, you choose a pair of qubits according to edges in this graph. You apply some random universal gate on them, okay? So this is a single step, and you keep going. And okay, some technical, okay, it's like some technical comments. So we don't need to assume inverses or like algebraic entries in this universal gate set, which maybe, I mean, it kind of follows from some okay, so because we build our results on some random quantum circuit literature, especially paper by Bandao, Haro, and Horodecki, but also this mathematical paper by Peter Value, and some, let's say, further work I did some like 1 or 2 years ago with Michal and Adam. Okay, this is just some technical comment. So formally, our unitaries are distributed according to essentially convolution of the of this generating measure, like t-fold convolution. That's so So we build random sequences of gates according to, like in each step, we couple some qubits according to connectivity in our graph. We keep on iterating, yeah. And now, property that is crucial for my analysis is property of that we call approximate equidistribution property. So the idea is, as you iterate your random circuit, it would be covering more and more uniformly the space of all unitaries that you have. This notion is an attempt to capture this, like how uniform this uniformity on some specific scale epsilon. And the scale epsilon will be actually tailored or related to complexity scale on which I would be looking at. Yeah. So just to set some notation that will be used later. So space of unitary channels is a Lie group. It has some compact Lie group. It has normalized Haar measure. Normalized in a sense that it assigns 1 to the whole group. And we can talk about, with respect to our distance, we can talk about balls, like metric balls in this space of unitaries. And now I'll be using this vol of epsilon to denote Haar measure volume of those balls. And because of invariance of Haar measure, of course, center of the ball doesn't, where the center is, doesn't affect the value of the volume. And okay, just one comment, maybe more for quantum information people. So like people typically assume that this volume of those groups is just, okay, just some A epsilon to this d squared minus 1 is the dimension of the group. Like people assume something like this. And for epsilon going to 0, it's actually, or can do some things like this, but rigorously speaking, story is a bit more complicated, and like one can only give bounds in this form. Okay, like if you are interested also in large epsilons, it's yeah, just comment. And now I talked about Haar measure, about volumes of balls, and now I take another measure, mu, in the space of unitaries, and I'm fixing parameter epsilon, and I'm fixing 2 positive real numbers, alpha and beta. Alpha is supposed to be slightly smaller than 1, beta is supposed to be larger than 1. And now I would say that this measure nu equidistributes on scale epsilon with those parameters alpha and beta, if and only if for every ball in my group and for every radius that is larger than this parameter epsilon, volume computed according to my measure, okay, can be lower and upper bounded by volumes of Haar volumes of slightly larger and slightly smaller balls. Does it? So this captures quantitatively on scale epsilon that my distribution is uniform when my reference uniform distribution is Haar measure. Okay. Okay, it looks maybe formally and like mathematically this definition, but actually all the proofs I'll be presenting just rely on them, on this property. Okay, it's quite convenient, it turns out. Any questions about it? Okay. So what is the structure of our results? So recall that we have those random circuits generated by local random circuits of some depth t. And now assume for the moment that I know that this measure after t steps equidistributes after some number of steps t equidistribution. Let's say for fixed parameters alpha and beta. Assume that this is true. Now, from this, we are able to derive the following results. So first we prove saturation of complexity for of unitaries generated in this random process for times that are larger than this equidistribution time, larger or equal. Second, we prove that it should be the other way around. Apologies, but qualitatively is the same. So just we prove that that recurrence, that is to say, drop of complexity happens with high probability in this double exponential time. Just from this property, we are able to prove it. And lastly, we are able to connect timescales on which recurrences happen to exactly timescales of this equidistribution. And now, but how do I get there? And I won't be talking, this is actually the most technical part of the work that I won't be talking except for this slide about it. So first, there is this notion in quantum information theory called approximate unitary design or approximate K-expander. And one can actually derive conditions that this approximate unitary K-expander has to satisfy for it to approximately equidistribute. So just very briefly, this unitary K-expander is defined as a measure on the unitary group that agrees with her measure on when it acts on polynomials of degree at most k, polynomials in entries of unit types. Okay, as I said, it's a bit technical. Later in the discussion, I'm happy to talk more about it. But okay, so we connected expanders to equidistribution, but we need to connect to random quantum circuits. So the way we do it, we use some bounds, maybe certain generalized bounds that govern long-time convergence of random quantum circuits of the form that we defined to approximate K-expanders. So we know how many times we need to iterate to get delta approximate K-expander. So we can now just sort of plug in the those conditions into here, and that gives bounds on equidistribution time. So there are maybe two variants of those equidistribution times I wanted to highlight. So one is the just general bound that doesn't assume anything about whether we have inverses or not in our gate set that was defining the random quantum circuit. So qualitatively they are sort of the same, but both formulas are the same. But here you have some annoying, let's say, you have this mild dependence on epsilon, crucially, okay? But here it's to the power 5. here, oh, there is a typo. Here you don't have it. So it's like log 1 over epsilon and something exponential, okay? So let's say take-home message from this complicated slide is that there's for very general random local quantum circuits, equidistribution takes place in exponential time, really exponential of the system size, number of qubits, and it has mild dependence on this accuracy parameter epsilon. Okay, so we can now move to our results after this preparation. So, but maybe there are questions or comments. Yeah.
Actually, just one question. What is your definition of recurrence?
So recurrence, I will be formally defining this, but recurrence would be the first instance of time when complexity, let's say, goes to 0. I mean, one can make it more general, but let's say it goes back to 0. After, so it attains almost maximum at some point. And then I'm looking for the first, let's say, return time in the vicinity of identity channel.
You see, so this is not necessarily the notion of the state recurring.
I mean, okay, so I'm focusing for the sake maybe of clarity on the unitaries throughout my presentation, but we do have also results for states. One just has to change dimensions a bit because dimension of the manifold of quantum states is different than the unitary channels. And it would be, if I understand, like recurrence of a quantum state is like you basically look when your, let's say, evolution brings you back in the vicinity of your initial state, right? That would be the, like quantified in some way by some metric, right? So it will be the same. Yeah, it's an agreement, yeah.
So you really are, so you're getting back to the same unitary channel. It's
Yes.
not just, it's not
Yes.
just that you've got a different channel where the complexity also goes to 0. You really are.
I'm going back in the vicinity. So here, because I'm looking on everything at scale epsilon, roughly speaking. So for me, the recurrence would be like going back to the ball of radius epsilon around identity that has trivial complexity.
Good. Okay.
All right.
Thank you.
So first result is about saturation of complexity from equidistribution. We have the usual setting, and the result is like this. So, and actually I will be proving this to you in a second. So if I have some measure that equidistributes on scale epsilon, and there are those parameters alpha and beta, but I keep them, I mean, under the, like I keep them fixed. Then with, let's say, overwhelming probability, complexity of my unitary would be, essential scaling here is like d squared log 1 over epsilon. This is essentially the maximal complexity you can get in the system of dimension d. So we can prove that the complexity is lower bounded with significant probability by quantity that is sort of like has the same scaling. You have here just the size, logarithm of the size of the gate set. And this bound is essentially, I mean, is tight in a sense that your complexity really cannot be much larger than this. And it's, there is some standard argument about it. One can find it like in Nielsen and Chuang. Okay, this is one thing. Another thing that maybe I will skip in detail in the interest of time. So we can actually quantify how many in this measure, like how many distinct high complexity unitaries there are. And it turns out that there are plenty, almost as many as there are epsilon distinct unitaries in the full space. So just some picture about it. So we have unitary group, we have support of our measure, we have some space of low complexity unitaries on scale epsilon. And now we can, let's say, count like maximal number of distinct balls I can sort of pack in that are in my support. And this number is very large. That's all I want to say. I mean, I won't be proving this part. It's not hard, but let me prove still this or sketch the proof of this lower bound for complexity. It's not complicated, I think. So, so first of all, like we define a set of unitaries that have complexity smaller than R. Okay. So basically, this set is essentially a union over balls centered at circuits that I can generate from my gate set, and that would have length at most R. So here I am summing over lengths, right? So from 1 or from 0, it doesn't like, here I'm summing over words that have this specific length. Okay, so this is the set of low complexity unitaries. And now what I do, I just compute the probability that my unitary randomly chosen from the measure nu has complexity at most R. So it's just the same as computing the measure of this set CR epsilon that I defined above according to this measure nu. And now I just use the union bound to upper bound this this measure by sum of measures that I attribute to each ball that is centered in some circuit that I was able to generate by the circuit of depth at most R. And now I am invoking this approximate equidistribution property. So volume, like measure of every ball like this, is at most beta, this parameter in the equidistribution times epsilon. And then I just sum this, like there is some geometric series going on here, right? And I have also upper bound on the volume from this reference I showed you earlier. It scales exponentially with the dimension of the group. So probability that my circuit has small complexity is upper bounded by this quantity. And now I just impose the condition that this upper bound should be smaller than delta, and I solve for R this inequality. Okay, and it roughly speaking gives me just this, what I wanted to prove. So it's just using union bound. It's basically the same proof that one uses when one wants to show that how random unitaries have high complexity. Just we invoke this equidistribution here. That's the only difference. Shall I continue? Are there questions? Okay, I continue. Now, recurrence from equidistribution. So this would be a fun one. So recall that we are building our circuits from concatenation of local quantum gates. And now, crucially, we will be looking on trajectories, not on unitaries at specific time t, but on whole trajectories. And we'll be sort of trying to understand like complexity properties along that, along trajectory. I want to make some quantitative statements about recurrence time. So my approach is like this. So first, I want to make sure that with high probability, no recurrence happened, let's say, for K1 steps after equidistribution. So visually, I want to know, here I have this equidistribution, and I want to be sure that I remained large, okay? Oh, here is a, sorry, it should be, this is, sorry for this. So probability, oh, no. Maybe, it was, sorry, my bad, it was fine. No, sorry. Yeah, so probability that that there exists some time that there exists some time from tau to tau plus K1 that that complexity is small for some reason. I should ensure that this probability is small. Sorry, there was some typo in my presentation. So this is one thing I want to ensure. The second thing I want to ensure is that recurrence for sure happens, almost for sure happens within K2 steps when K2 is larger than K1 after equidistribution time. So within those K2 steps, I should have high probability that there exists some time t that my complexity went exactly to 0. Okay, so I want to have such quantitative statements. Okay, and we are able to provide them, fortunately. So just to change the, to rename things, so this K1 is a lower bound for my recurrence time, and K2 is upper bound for this recurrence time. So essentially, we are able to give lower bound for K1, so lower bound for the recurrence time, and upper bound for the upper bound for recurrence time. So this allows us to pinpoint recurrence sort of happening sometime within this region here, like between K1 and K2. Okay, and now, so essentially I set some level of complexity R that is essentially maximal. Here it is. And I set, in my result, I set some values of my, let's say, of those times K1 and K2. So this K1 is like any parameter that is like smaller than this. Notice exponential scaling with the dimension. So with the number of qubits, it's double exponential. This K2 is larger thing. It's multiplied by tau, by this equidistribution time. And you have those parameters, they kind of, okay, capture the probability that it's not that like a failure, essentially. Okay, and now, so first result is that I like with significant probability, complexity would remain above R for all times until K1 steps after equidistribution time. So large complexity during first K1 steps. The second thing is that like with significant probability or almost like maximal probability, in the first K2 steps, my complexity will go down to 0. So yeah, so those are like our results. Yeah, those deltas, they just quantify like probabilities that it's not like that the behavior is not as I'm describing. And it makes sense because like everything here is random, so I have to allow myself some space. Now, I will attempt to sketch the proof of this result. Let me just so this first bound is actually the proof of it is just identical as the previous saturation consideration. So I'm gonna skip it. So now we are interested in the like sort of ensuring that if I wait long enough time, my complexity almost for sure will go to 0. So how to prove it? So I look on the opposite event. That is to say, I want to now ensure that for all times in this window from tau to tau plus k, my complexity is actually larger than 0. And I will be showing that probability of this becomes small. Yeah. So first thing that I do, I decide to like look on my system in a stroboscopic fashion. So rather than looking on every time of my evolution, I look on every tau steps. So remember that tau is my equidistribution time. So I'm crucially will be using this property here. So probability that for all times in this interval, my complexity is larger than 0 is smaller than the probability that, you know, just in every tau steps, my probability, my complexity is, is large, okay? And now, intuition is, and one can make it sort of precise, that, you know, because this measure after L1 plus 1 times tau steps is the same as convolution of my measure of tau steps and this measure like after L times tau steps, because of the fact that this probability, this measure equidistributes, effectively events that occur every tau steps and have to do with distance scale epsilon, the way I defined, okay? They behave like independent events. This is some intuition and one can make it precise. Like you can sort of think that on this time scale tau, you are implementing almost Haar measure, okay? From the perspective of bounds that you are gonna obtain. And right, so basically here I have almost like the same, like identical events. Ah, sorry, it's this. Okay, so I can now upper bound this probability that for every time in this big time window, my complexity is larger than 0. I can upper bound it by the product of the probability that after just tau steps, my complexity was non-negative. And I have to iterate here, k over tau times, because I'm looking on my system every tau steps. And now I can invoke equidistribution to upper bound this quantity by the volume now of the smaller ball. So this is essentially probability that I'm outside the ball of radius epsilon. So I can, so it will be like 1 minus nu of this ball. Okay. And now I can upper bound this quantity because of my equidistribution property. And again, demand that that this whole event should have probability at most delta. And if I unpack this relation, I will get this bound on K. Right. So essentially, I'm looking on my events every tau steps when tau is equidistribution time. This allows me to upper bound the probability that complexity remains non-trivial for the whole duration of this window from tau to tau plus capital K. Okay, so that gives the recurrence that I wanted. Now I'm looking on. So I guess we have maybe like 5 minutes. So I'm maybe just I won't be proving this. I mean, I just maybe state, right, that yeah, I mean, okay, like if you are interested, we can talk about it in the discussion because I don't want to stretch my, yeah. So essentially now, if we look to get timescales of recurrence, I actually need to have a peculiar relation between this alpha and beta. They have to be really close to each other, like exponentially close. And now, so here's the, all right, okay, so what I want to say, just conceptually, how I understand this timescale of recurrence. So assume I got to trivial complexity at some point t. And now I can look in the past and kind of look like what is the probability that after some time steps in the past I had high complexity. Likewise, I can go to the future, like what is the probability that given I had trivial complexity here, I came back to high complexity. Like basically this part is kind of trivial because I can just repeat my reasoning from saturation part, but this part is kind of non-trivial. So what we are able to show is essentially if this now if I set this past time to be on the scale of this funny equidistribution scale, equidistribution time with those funny parameters, and if this time t when I assume the recurrence happened, that is complexity went to 0. If I assume this time is large enough, still exponential but large, then I can ensure that conditional probability that after tau p steps in the past, I had high complexity, given that at time t, I had trivial complexity, I can prove that this conditional probability is almost 1. Likewise, I can prove for the future. So all in all, that gives me that this time probabilistically, this time that recurrence took place scales exponentially with the system size, and like log 1 over epsilon, when epsilon is this accuracy parameter. This was another, let's say, small another thing that again Susskind conjectured in this recent black holes are at exponential time paper. At least one can read it between the lines, or this is how I understood some of the things there. Okay, and it's okay. It's maybe funny because like this shape is supposed to correspond to what, like this behavior of Penrose's diagram of the wormhole. Okay, I understand it on mathematical level here, of course. No, I don't understand gravity. I skip the proof sketch and go straight to conclusions. So we studied complexity behavior, long-time complexity behavior of local random quantum circuits. Hopefully we managed to get, we did prove saturation, recurrence, and timescales of recurrence of complexity in this model. And the key tool was this new property of approximate equipartition that allowed us to prove all those results. But to get to this approximate equipartition property, we use properties of random quantum circuits. Like exponentially deep random quantum circuits form good enough expanders for our construction. I conclude with some open problems. So I guess proper linear growth in early times, it's still an open problem. It would be nice to extend our results to other models of chaotic evolution, like based on continuous time random walks. Still, free Hamiltonian evolution, it's an open problem as far as I know. Like there is no concrete example of such a curve for any model. It would be intriguing to maybe connect this approach to Nielsen geometric approach to complexity of unitarison states. And explore maybe the connections to black holes, if there are any. Yes. So with that, I wanted to thank you for your attention. That's it from my side. Yeah.
Great, thanks. That was an awesome talk. Do we want to start with some questions? Okay, I'll start with a question. I really like this paper in particular because it's talking about this approximate notion of complexity, which I think is definitely the sort of the right or more natural one to use. But I'm very interested in this early time behavior and whether you think that any of these tools might help us prove sort of results about approximate complexity there.
So this equipartition, I don't think so personally.
Okay.
So, I mean, because basically short answer is that I don't think so. I think that maybe better bounds on gaps of random quantum circuits can, maybe I don't see, because essentially the requirements that you have for this approximate equipartition property, in terms of degrees of designs, they are huge because they're like exponential.
Right. And do you know if there are complexity barriers to, like, unless P is not, you separate P from NP or something like this, if you could show the early time behavior of approximate complexity?
I mean, good question. Good questions. I know that there are some, but I don't know answer. I know that. I mean, some results along those lines are like Aronson discussed them, but I'm not versed enough to, yeah.
Right, but they always have these sort of conjectures, right?
Yes. They all, it's always.
Yeah, I'm just wondering if we could hope to unconditionally solve this problem, without making some major advance in complexity theory. I should know that myself, but embarrassingly, I don't actually.
Yeah. No, I cannot say anything concrete from the top of my head, unfortunately. Yeah.
Okay. Interesting. Anyone else?
Stop the recording. Okay.